Hello everyone! This is a video about the derivative. I'll be using three different constructions. I will introduce the classical derivative, a Lie algebra variant, and a linear algebra variant. With these constructions, I hope to build creativity, connections, and further intuition. I'll provide timestamps so you can skip around. However, I genuinely believe that everyone can get value from each section. And if you don't, make sure to critique me in the comments. Be nice though, this is my first video. To understand derivatives, the best place to start is with straight lines. Here is an equation that relates an additive change in domain, or x, to an additive change in range, or y. It reads, y of the sum of x and change in x equals the sum of y of x and m times delta x. I'll be referring to the two sides of the equation as the change in domain form and the change in range form. For those who have taken an algebra class, you can kind of squint your eyes and get y equals mx plus b, where the green is y, blue is b, and red is x. Functionally, it is the same except you are setting the y-axis to be at the original input and taking the change in x, or delta x in this case, to be x. The letter m is just a constant, and it is equivalent to a conversion factor between delta x and delta y. Multiplying delta x by m turns it into delta y. This way, when you add m times delta x to y, you are equivalently adding delta y to y. Great, so how does this fit into derivatives? Well, look at the straight line I provided. Can you notice anything abnormal about it? If you can't, that's a good thing. That's what I intended. It'll help explain the next bit. The special thing about this straight line is that it is in fact not one. It's a curve. I just zoomed in really close. This goes to show that a lot of curves are approximately straight lines when you zoom in. And when you zoom in, the equation of the straight lines are still useful. Only now instead of m being constant, it changes at every point in the curve. The function that describes m at each point is called the derivative, and the notation is often represented by adding a prime or apostrophe to the function it's differentiating. So, how do we use this definition to derive properties of the derivative? Let's start with the product rule. Given the product of two functions, f and g, with change in domain form, and h to represent change in x, if you substitute each equation's change in domain form with their change in range forms, you get a product of two linear equations. Then just expand it and gather like terms. There then exists three terms, one constant with h, one linear with h, and one quadratic with h. It's this linear term that is tied to the derivative that we defined earlier. The chain rule is slightly more complicated to explain. Given two functions, f and g, where g has a change in domain form and g is used as an input to f, you can modify the internal change in domain form to be similar to a change in range form. The key insight here is implied by how I colored the three equations. It's that this new form, with g, is also approximately a linear change in domain form for f, assuming h is small enough. Then you can substitute in this change in domain form with a change in range form. Then you just have to pull out the term tied to h. When there are more functions nested, the resulting equation kind of looks like a series of rushing nesting dolls multiplied or chained together in a line, where the outermost doll of each hold a prime while the inner dolls preserve their form. Now, a more advanced approach involves the Taylor series. Instead of having only a linear form, the Taylor series takes a more polynomial approach. The equation takes the change in domain of y to be equal to, across each n, the summation of the nth derivative of y of x over n factorial, where n is a whole number. This form is more accurate for larger changes than the simple linear form. For the product rule, this extends to the previous mathematics well for higher derivatives. You just take the product of the two series and pull out the corresponding term for higher order derivatives. And if you're clever, you don't even have to evaluate the whole thing. For the third derivative, the corresponding term is h to the power of 3 over 6. Once you have all the terms, you just divide by h over 3 over 6, and you have the third derivative. For the chain rule, it's significantly more complicated. Take f of g. You can create a Taylor series for each, where f uses change in g for h, and g uses change in x for h. The hardest part is that the change in g is actually the difference of the Taylor series of g and g. So you have more terms involving squares and cubes, and more of an infinite series. And none of it is really fun to describe. For the third derivative, take all the change in g terms cubed and less, and iterate through each. For the linear change in g, you'll need to pull out the h cubed term. For the change in g squared term, you'll need the h squared term and the linear squared term, the product being h to the power of 3. The two terms are counted twice, like in the FOIL rule or the binomial theorem. The final change in g term is cubed, so you just need one h linear term. Then just multiply by h cubed over 6. Another way to build the derivative is by using Lie algebra. To begin to understand that, I'll have to explain the mathematics of Lie algebra. In the simplest description possible, Lie algebra is an area of math that brings into focus the commutator. The commutator measures the degree in which the order you multiply two objects together matters. The commutator of d and x is d times x minus x times d. Note here that although I heavily implied that d and x are related to differentiation and the object x, I have yet to define them so. I will do that later. From the definition of commutation, there are several properties that are simply derived. If you swap d and x in the operation, this is equivalent to multiplying by -1. In a sense, this sort of implies there is a kind of symmetry between the differential operator d and the object x. This is one of the many fascinating and useful behaviors of differentiation that many people might not even know about. Another property is that it is linear. This matches closely with the already known properties of differentiation. Another property that you can figure out with a little bit of algebra is the product rule. The result being that the commutator of d and a times b is the commutator of d and a, all times b, plus a times the commutator of d and b. Note here that the order of a and b and the commutators are all important. This is because we are working in an algebra where a times b may not be equal to b times a. I find it amazing that linearity and the product rule are within the definition of the commutator without ever actually mentioning slopes or derivatives or tiny changes. It mirrors that behavior from entirely different core behaviors. The chain rule in Lie algebra is more complicated. Here is a more general equation. This equation, although unrelated, kind of looks like the difference expansion from the Taylor series section. However, unlike that difference expansion, the derivatives are on the far left of each product instead of the right, and instead of powers of change in g, we have a d repeatedly recursed in commutators of g. Interestingly, if we define the commutator of d and g to be hd, then it would become the difference expansion multiplied by d on the right side. But that's a digression. I highlighted the term on the left-hand side of the equation because I wanted to emphasize that the chain rule is built in here. In fact, if g commutes with the commutator of d and g, then it becomes the chain rule. And if you define the commutator of d and x to be 1, then you essentially have defined an alternative to the derivative. This is one of the many things I love about math. In entirely unrelated areas of math, equivalent results can often appear, almost like how pi keeps reappearing in random places. Another thing to note is that there is a symmetry in the result that also applies with d. At this point in the definitions, d and x are interchangeable. With all of this, we can finally officially define the derivative using Lie algebra. Abstractly speaking, if you take the concatenation of an object adjoint d and f of x to be the commutator of d and f of x, then the adjoint d concatenated with f of x is equivalent to the derivative of f of x. Fun fact, the adjoint of d actually behaves the same as d when in the commutator. And if you so choose, you can define d to be the adjoint of d. This may be odd and super abstract, but doing so allows the multiplication of d to be equivalent to differentiation, and you can use the commutator to algebraically manipulate equations, swapping the orders of multiplication. This legitimizes all sorts of powerful things, like putting differential operators in functions. at least as long as it's multiplied by a differentiable object. The final reason I'm introducing a Lie algebra definition of differentiation is because it creates a correspondence between differential operators and domain transformations. Just like the correspondence between Lie algebra and Lie groups, it shows that for any domain transformation, there is a differential operator with similar properties to the derivative. All the neat things you can do with calculus, you can do with these alternative calculus. It also allows you to create a mathematics of domain transformations. So instead of differential equations, you can have domain transformation equations. You can define summation, continuous recursion, titration, and even look at fractals from a new perspective. All fun and fascinating stuff. The final representation I plan on showing you is short and sweet. In the previous section, I showed that differentiation could be represented as multiplication. This takes that literally. This representation borrows from the ideas of linear algebra and matrices. And while there are actually a lot of ways you can represent differentiation using matrices, I actually won't be showing those because they have a lot of limitations. But I do think it's worthwhile if you have the time. Instead, I'm going to pull an idea from linear algebra that I think works very well with differentiation. The last section is about eigenvalues and eigenfunctions. So what is all this eigen stuff? Well, let's say you have a differential operator d and a function f. If you multiply d and f, then under the behaviors of f, d can be thought of as transforming into a constant, lambda. And that's it. Why is this such a great representation? Well, unlike differential operators, constants are easy to manipulate. You can take a square root of a constant, you can take a log of a constant, even a factorial of a constant, and it's easy. And when you include integration and constants of integration, this methodology becomes infinitely more interesting. But integration really isn't for this video. As for what f actually is, it's also super simple. It's the exponential of lambda times x. This is because the derivative of the exponential is itself, and by the chain rule, it pulls lambda out of the exponential. Since this section is so much shorter, I'll leave you with an application of this method: quantum mechanics. So one of the core axioms of quantum mechanics is that energy is a particle's wave function waving across time, and momentum is a particle's wave function waving across space. And this is represented using this formulation of differentiation. The eigenvalues being energy and momentum, and the eigenfunction being the wave function. Applying the differential operator I h bar d over dt to psi, the wave function, gives energy times psi, and applying the differential operator negative I h bar d over dx gives momentum. So in any equation you have energy and momentum. You can apply this substitution, and you get an equation in quantum mechanics. For the classical non-relativistic energy relation, you get the Schrödinger equation. And for the relativistic energy momentum relation, you get the Klein-Gordon equation. That's all for now. In the future, I'll probably create an integration video, and I hope to create a series as well. I hope you've enjoyed this video.